Hi everybody, let me explain you how the testing strategy will change in the upcoming years as we move into an electrical world. So we have a certain ICE mindset, and I believe a lot of those insights which come out of the combustion engine environment, they simply cannot be transferred to e-traction testing. It starts with the engine itself. The combustion engine, when we compare it with an electrical motor, is much more complex. Means the electrical motor is much simpler than an engine actually. And also the transmissions in electrical drives are much simpler than in a combustion world, as pure electrical drives don't have clutches at all. We have very simple gears and transmissions and so on. Sometimes they are completely missing if we think about wheel hub motors, for example. So mechanics becomes much simpler. And what's new in a pure electric environment is that we have torque sharing between e-motors. In a combustion world, you usually wouldn't have more than one engine in a car. I know of just one or two examples in the past where you had vehicles with more than one combustion engine. In electric cars, this is quite often the case. So you quite often don't have just one electric motor. You have two electric motors, three electric motors, four electric motors, front axles, rear axles with motors. This means we have a torque sharing situation in electric cars, and this must be tested, and there are some very interesting effects which must be really done a lot of research and development to have no fourth fight and to make the torque sharing in a perfect way. Also, what's new in this electric world is that we have now high voltage power cables, not just one or two cables. Quite often when we have more than one electric motor, a cable network somewhere in the car. And these cables have interferences with each other. They have interferences with the structure. There's a lot of research needed on EMV behavior, EMC issues, and so on. What's also new is that over those cables now we have energy transmission, and people sometimes think, well, that's just a cable, 0 ohms, that's just a connection to bring energy from one point to the other point. However, it's not that simple, and I would like to compare it with a mechanical shaft in the mechanical world. A mechanical shaft also transfers mechanical energy from one point to the other point. But every mechanical engineer knows that such a shaft has its own characteristics. Depending on stiffness and length, you might have oscillations on the shaft and other nasty things which must be handled. In electric systems, it's the same. So the cables in between are not just 0 ohm connections. They have resistance. The resistance changes not only with temperature, it changes also with the frequency of the signal running on the cable, due to skin effects, to the proximity effects, and many more. Also we see inductance in the cable, and the inductance correlates not only with the length, it correlates with the size and how the cables are separated from each other. They create an inductance path, and if you increase the distance from the cables, then inductance rises. So very nasty effects. Then we have stray capacitance to the chassis and much more. So what I'm saying is that the cable and the cable network is a component for its own, and it's important to do investigation on that. This is a new testing focus which wasn't there before. So When we look to a combustion engine, I would say this former combustion engine nowadays in an electric world splits into two components. First, the electric motor, which is well known to everybody today, and on the second hand, to the power electronics. So the power electronics and the electric motor makes the drive in the end. So replaces the combustion engine. And the power electronics is a completely new component. Electric motors are known for quite a long time. Even though electric motors in cars are very specific, in principle they're known. So inverters in cars are, let's say, quite new. And I believe in such an electric drivetrain, the inverter actually is the point where we find the intelligence in the whole drivetrain, because simply of the software. So there's no motor with software, no software in the motor, and in the inverter you find a lot of software. In an inverter, typically in a drive inverter, you find 500,000 to 1 million lines of code, which means complex software which must be verified, and the inverter is key of optimization, drive behavior, and many functionalities. Also, what's new is a good point in electric drive. In electric drive, we can clearly separate the mechanical world and the electrical world. This was not possible in a combustion environment. When you wanted to have power, you needed to fire an engine, and you had always these things together. In an electrical world, we can separate that. We can see an e-motor, we can see gears, shafts, transmissions, chassis. This is the this is the mechanical world. On the other hand side, we can see a pure electrical world, which is just cables and electronics. It's a traction inverter, and then we have the battery with some chemistry in it. We have power cabling, as explained before. We have some more converters and chargers. So we have two worlds which we can separate, a mechanical world and a pure electrical world. And separating these both worlds makes testing much faster, it makes testing simpler, and it increases the test coverage of testing, simply because the complexity drops and we have no limitations from the other side. This means in the electrical world, if we do testing there and keep it separated from mechanics, we don't have the typical mechanical limitation. I just want to mention the hill setup in this slide as well. So when we are talking about power electronic components, and the traction inverter is definitely a power electronic component, hill-based testing, which is usually signal-based testing, is often obsolete and not needed anymore. What is needed today for power electronic devices is a power hill, and this is part in the electrical world. So how can these both worlds be separated? First, we have the separation process. We replace components with emulated components. Means we replace the real battery with a battery emulator if we want to test an inverter, for instance. And we replace the electrical motor with a e-motor emulator in such a case. And by doing so, we can separate the mechanical world and the electrical world. And this is illustrated with the red dashed line. Above you find a pure electric world, and below you find a mix of mechanical and electrical world. So in the upper world, which is pure electric, it's important to see this is really pure electric, which means no mechanics inside, no shafts, no rotating parts. We can do all tests for the power electronics for the inverter already under full power. And the key to this are the emulators. which means we can run VLTP cycles in a pure electric world with power. We can evaluate efficiency of the inverter. We can do optimization on the inverter and performance testing on the inverter. We can do software release testing. As I mentioned already, we have very complex software in inverters. We can do fault handling in a very good way. All this without the need to have a mechanical world involved or rotating shafts, which would be the case later when the inverter is tested in a profound way already. So now let's also have a word on Formula One testing. You see on this slide a racing car, and a racing car has an electrical system involved as well with two electrical motors. It's the kinetic motor for the cars and the turbocharger, electrical turbocharger for the heat system. So two electrical motors and a battery as well, and then we have an inverter driving those motors. If we want to test the inverter, we can make a setup as shown here in the slide. We can replace the heat motor with an emulated heat motor, and we can do so with the gas motor. Also the battery can be replaced sometimes with a battery emulator. And we have then a very nice setup. So in this slide, you see the red component is the unit under test. It's the only real component. That's the only real one. We don't need any mechanics here. We don't need real motors because they're replaced with emulators. And we can have a racing car simulation behind the engine and the wheels and the gearbox and whatsoever. We could have a real-time simulation behind. And the unit under test, as said before, is the MGU inverter. So in this diagram you see how it looks like. On the left hand side, the E-motor emulator for the heat motor. On the right hand side for the kinetic motor, you see three phases going to each of them, and a battery emulator supplying the DC link for the inverter. And we have a power cycle which goes over the grid. We're calling this a grid power cycling system, GPC. We could have a similar setup on DC side. We're calling this a DC power cycling. We do not need to go over the grid. We can cycle the power on DC side as well. In the end, the results are the same, but the setup is, let's say, smaller, but does not allow to incorporate a real battery. This is why there are two approaches, the GPC and the DPC. And what actually the advantages if we do that? So first of all, as said before, we have a very reduced system complexity. We have no rotating parts, we have no real E-motors, and it's not easy to incorporate a real E-motor for a heat system, for instance, because those motors are running at very high speed. We are having inverter protection because the emulators control the current, so this means inverter blows not so easy. And we have the possibility to really evaluate the inverter strategy here. So we can have a very high test coverage considering the power electronics, the inverter. We have no mechanical drawbacks, so it's pure electric, and the test procedures are much faster than in a world where we have mechanics involved. So we quite often cope with overheat situations, problems on the motor, problems in the shaft and the gears and so on. In this testing concept, we can completely get rid of this. So we can test the power electronics and the strategy in the power electronics without all the mechanical drawbacks. And perhaps one of the nicest point here is in the last box. This is, let's say, FIA regulation friendly, because in such a setup you don't have any limitation in the testing time, and you can cover all inverter-related test scenarios. So this was a short introduction how the testing strategies will change when we come from a combustion world into a pure electric world, and I hand back to the moderator for the next interesting topics.